the new coupled models there with OpenIFS and our own finite volume CIS ocean model. Yeah, so this is a short overview. I will give a little bit of introduction to our CMIP6 model. Yeah, I think I will not use the pointer because then online people can't see the pointer, right? I will use the mouse. But yeah, so there will be like a slide on our CMIP6 model, RVCM1, our first coupled climate model, and then RVCM3, sort of our new development, skipping one cycle in between. Then some lower resolution and middle resolution simulations, and then some high resolution example case. Some ideas that we have about perhaps contributing to OASIS with stochastic coupling, and then a little bit of an outlook of system model development that we're doing joint with other communities. Okay, yeah. So RVCM1 is one of the, let's say, main AUGCM configurations that contributed to CMIP6. So here's 30 of them. I've sort of left out the Earth system models that are based on these AUGCMs, and these are hopefully fairly standalone models. And you can see, okay, there's a lot of them, and we are one of them. And what makes us special is the way that we do the ocean. So what I show here, I have to show, of course, with the mouse. What you can see here is that we have an unstructured mesh ocean model, and I think we were the first ones to have it globally. So you can really put the resolution where you want, and not everywhere else where you don't want it. So for example, you may not want to have the same ocean resolution in the middle of the subtropical gyre as you want in, for example, the ACC or in the Gulf Stream. What I show here is a toy mesh where the individual cells are large enough so that you can see them on the screen. In reality, the simulation resolutions are higher. So for FESOM1, for our CMIP6 model, we had something between 100 and 10 kilometers that were practical, maybe not on the same mesh, but that's the sort of range that we were having. And then on top, when we coupled it, we had ECOM6, which is the Earth climate model from Hamburg, from the Max Planck Institute, which had a practical resolution of either 200 kilometers for the TCO63 or 100 kilometers for the TQ127. And we saw that with our flexible mesh, we had, this is well documented, okay, we have several papers on this and also a paper on the CMIP6 version. And then we developed our new finite volume ocean code. So the first one was elements, next one is finite volume. And this ocean model had, for the same sort of climate fidelity, it was around 3 to 4 times faster than the old one, FESOM1. So that we reinvested into higher resolution. We now have meshes that can be much more highly resolved than the previous one. But if you have a 1 kilometer ocean model and then you have a 100 kilometer atmosphere on top, that's quite a mismatch. And so we were looking around for a new atmosphere. We also knew ECOM wasn't going to develop any further. The new Icon atmosphere wasn't quite ready yet. And so what we ended up doing is we went for OpenIFS. OpenIFS, that is a more readily available version of the IFS code from ECMWF. And here we have the opportunity to use much higher spatial resolution, mostly because the time stepping scheme is capable of much larger time steps at the same resolution due to this semi-Lagrangian tracer affection. So you can get information that is sort of in a normal Eulerian model would vary in a condition. And now we have, again, models where we can have kind of similar resolutions on the ocean and atmosphere side, and we can hopefully really play out our resolution advantage compared to some other models out there. And this was recently described in geoscientific model development. So in the first version of this new, we call the RVCM3 model, we more or less implemented, again, the same coupling algorithm that we had in the previous version, and we just swapped out the models, more or less. Okay, so this is what it looks like. We have the FESOM Ocean, which has its own sea ice model in there. Then we have the OpenIFS atmosphere, which comes with a wave model and a hydrology model inside. We have a little runoff mapper, which we borrow from the Easy Earth community. And it's all coupled with OASIS 3 MCT5 in this case. And currently we're using for the fluxes, so from the atmosphere to the ocean or through the runoff level to the ocean, Gauss-weighted, sort of the nearest neighbor with a little bit of weighting, and then afterwards a conservative post-processing to make sure that the global fluxes are conserved. And in the other direction for ocean to atmosphere, we have a mixture of Gauss-weighted and bicubic relations, and then the output through XIOS from the atmosphere. And then, so that was basically just re-implementing what we had for CMIP6, sort of old stuff. 10 years ago, we first started doing this. And then in the next step, we went back and said, okay, let's have a look at the assumptions that we made many years ago when we started model developing in terms of what we actually send in, right? So talking about what the coupler is doing is one thing, but we have to use the coupler correctly, right? What kind of fields do you even give to the coupler? And so there's a couple of them. The first one, actually, enthalpy of fusion of snow falling into the ocean. That was something that we had missed. It's pretty trivial. But previously it was done on the atmosphere side in one model, on the ocean side in another model. And we just forgot about it when we made the first version of ICM3. It was a pretty significant error that was in this first published version. But then there's also some other smaller things. For example, mass and enthalpy of icebergs that are melting. So we now have an iceberg model inside FESOM in this newer version. We have also, can have at least an approximation of what kind of heat flux comes together with rainfall, because the temperature at which rain falls into the ocean might not be the same as the ocean surface. So that can also be a watt or two per square meter. And then we recently also activated current feedback. So in the previous model versions, the ocean surface was always assumed to be at rest. And now it is no longer, it is moving, and the atmosphere is being told about what the ocean surface is doing when it calculates surface roughness and momentum exchange, etc. Okay, so in this new version, so this is the 3.1 version then, we did a deck experiment. So we ran 500-year PI control simulation and then a historic simulation at the end. And what I show here are Reiter and Kim performance indices for many different variables. Essentially, I downloaded from the ESGF nodes, all the data for those 30 models that I gave the long list in the beginning, and I calculated versus observation and reanalysis data, the mean biases, absolute mean biases. And then I did the same for our model, always taking the last 25 years of the historic period. And wherever our model is green, the biases are smaller than the average CMIP6 model. And wherever it's red, it's more, right? So you can see in some variables, we're doing quite well. And in other variables, we have some catch up to do, especially, for example, standard deviation of ocean surface temperature doesn't look very good. And this is what we would consider a paleoclimate ready version of our model. So we have a 100-kilometer atmosphere. The ocean, you can see here, it has a different resolution and different latitudes and a little bit higher along the coastlines, but that's it. And it's about 130 simulated years per day with this model, which we are hoping to use for sort of longer millennial scale or so on paleoclimate applications. I promised high resolution. That's certainly not it here. So, oops, that's 2 steps. Go only 1. So this is something that we are eyeing for a potential CMIP7 deck. This is a TCO 319, 30-kilometer atmosphere. And then the ocean model, you see now we have between 30 and 6 kilometers. And the resolution is higher in high latitudes where the Rossby radius deformation is smaller. But then it's also higher in regions where the sea surface height variability is very high in observational data. So it's sort of focused on the areas where the ocean is active, where eddies are small. And in the other regions, the resolution is lower to save some computational power. And what we can see, so this is a little bit of a caveat, this is not a full deck simulation yet. This is only 200 years with this model. So I wouldn't really vouch for the biases in the deep ocean at 1,000 meters or more staying the same. That's probably still a bit of initial state in there. But especially for the winds, for the surface temperatures, except for the Ninnu 3-4 region, and for clouds and precipitation, we can see that this model is quite a bit better than what you get for most CMIP6 models at the moment. And a lot of that is just higher resolution and better better fidelity from that, right? And ignore the deep red numbers for the mixed layer depth because we outputted the wrong density threshold here. So that's not the same as the observations. Oops, it's always doing that. Okay, so another setup that is currently being developed is this one. It's focused on the Southern Ocean. So you can see in most of the ocean we have now 20-kilometer resolution, but then in the Southern Ocean we have something between 2.5 and 3 kilometers. So the grid size, the total grid size of number of surface points is about 10 billion, quite large, but it's really focused on the Southern Ocean. And then you have an atmosphere on top, which is TCO 639, so it's a 16-kilometer atmospheric model. And there's no long simulations with it yet. We know that we can get about a simulated year a day out of this model, which makes it somewhat practical for a project. We certainly wouldn't want to do a full deck experiment with it. It would take several years, but it's usable. And it is usable because of the features that we have in OASIS 3, MCT 4, and 5, right? If we were not able to do a parallel generation of remapping weights, for example, we would not want to even generate the weights for a configuration like this. And the new load balancing features in MCT5 are really quite useful for balancing out.
OASIS 3 MCT5. OASIS 3 MCT5.
Yes. Did I say OASIS 5?
Oh, you said MCT5.
Yeah, I know.
OASIS 5. Okay, so I don't have a performance chart for this, but this is the sort of research you can do with this, and because we don't have really hard numbers for you yet, I can only do what all the people doing really high resolution simulations do in that case, which is to show pretty pictures. Okay, so you can have a very eddy-rich Southern Ocean even under the sea ice, which is something that you cannot do. You can see individual leads and cracks in the ice, which is quite nice and matches quite nicely what you see from satellite observations. Of course, not on the meter or 100-meter scale, but at least on the several kilometer scale. Okay, sorry, on the left you see surface current velocity. On the right you see sea ice. Okay. So one of the things that I have talked about a little bit is we have this mesh which has different resolutions in different regions on the ocean side. And this can lead to quite a large different ratio of atmosphere resolution to ocean resolution. So if you were to look at one atmospheric cell, how many ocean cells do you have underneath, right? And specifically for the Southern Ocean example, we have in some regions, for example, at the equator, an atmospheric resolution of 16 kilometers and an ocean resolution of 20 kilometers. So you have 0.6 ocean cells per atmospheric cell. But then in the Southern Ocean, you can see here the TCO grid, when they say 16 kilometers, means 16 kilometers here at the equator, but you might have 19 kilometers at high latitudes. And at the same time, you have a 2.5 kilometer ocean underneath, which means you have in excess of 50 ocean cells for every atmospheric cell. So there's a tremendous amount of information available at the ocean surface. And the question is, are we using that in the atmosphere? And with the current Gauss-weighted nearest neighbor, we kind of don't, right? We can increase the number of neighbors that we include in this Gaussian weighting, but anyway, it will always be focused on the middle one, unless we make the Gaussian, if we make the kurtosis of the Gaussian distribution wider and wider until eventually we get the unipolar, basically like an arithmetic mean over the cell, then we have all the different cells included, but that's really bad because then you lose all the subgrid scale information. You just make a big mean over a huge blob of ocean. That's not actually helping either. And we know that this doesn't help because we have publications where we have tested this. Right? If you just make an arithmetic mean over these 50 boxes, it's worse than just taking one. And the idea that we're having right now is maybe we can have a sort of stochastic coupling. If we have a certain number of grid cells underneath, why don't we select stochastically from what we have rather than to make some kind of arithmetic mean or to pick the middle one or something like that. And the idea here, and this is pure code scouting and speculation at some point, but the idea is to go into the OASIS coupler, take the remap conserve and make a remap stoch where you use the frag area algorithm to sort of bin and find out what cells are underneath your ocean cells, so what ocean cells are underneath your atmospheric cell. Then instead of creating weights for it, you just give everyone a weight of 1. And then at runtime, you modify your SMAT-P, which is your interpolation matrix, and you kick out all but 1. Right? You would have to do the binning again, and we would have to really check if that's a big performance issue at runtime to do this sort of binning again. But in that case, you could stochastically pick different points underneath your atmospheric cell. And you could pick this ocean cell or that ocean cell or that ocean cell. The first question, of course, that everyone has is, well, but that's not bit reproducible anymore, right? What are you doing then if you can't check if something goes weird? And the idea would be perhaps we can do something like seed with the incoming values that we have from the binned area, and then that would hopefully be able to be a bit reproducible. But that's something we will find out if we get to it. And then there's lots of options what you can do later on with the stochastic process. Once you have it in, you can build some kind of fancy Markov chain on it, or to make sure that you're not crazily jumping around, but you're like sort of snaking through, either through data space or through spatial space, whatever you want. But first we would need to solve the technical questions, of course. Okay, and then one last slide. This is a lot of AOGCM stuff now, but we have also another section, which is the paleoclimate section in our institute, and they're more working on Earth system modeling, so coupling further components in. And building an entire Earth system model is too much. We're not a small institute. We have like 50 people, but I still wouldn't say that we are capable of sort of Max Planck style complete Earth system model development. So we're quite happy that there's overlap with other communities in Europe. Chiefly with the EC-Earth community. You see in the center column what we envision ENES-RI to look like in, say, 2-3 years' time. We have our own ocean and ice model here. We have this biogeochemistry model developed at RB with a PISM ice sheet model, LPJ gas vegetation model, developed at Lund mostly. And then the OpenIFS XIOS, and I guess this says runoff mapper, but I hope that it will be camouflage, actually. And you can see this is a complete overlap with EC-Earth4, actually, right? So the only additional thing is that EC-Earth4, for their standard configuration, they use NEMO4 and SI3. But there's a lot of overlap where, on the one hand, we can gain from having, for example, the dynamic vegetation model from them, which is very important for paleoclimate applications. But on the other hand, we have a lot of expertise in the cryosphere where we can help them build a better cryosphere model. And then there's also another overlap, which is this year with the FOSSI OpenIFS. This is a completely different AOGCM on very similar components currently developed at GeoMar, which is also in Germany. It's another Helmholtz Institute. And I don't know how I am on time, but I am done on slides. It's time for questions and comments.
Okay, so I will talk a little bit about some experimentation we did at ESMWF, where we try to sort of push the envelope quite a lot in terms of what we would normally do. So this, and we were able to do that thanks to the INCITE project, which was so.
You first have to click the mouse.
Then great. So I'll talk a little bit about what this whole INCITE project is. I'm also going to go through our modeling system. It has kind of already been mentioned what we're doing by other people, but I'll go through it. And then I'll talk a little bit about how we run coupled model on two systems with this INCITE stuff, our own local new ATOS machine. And the INCITE is actually at U.S. Department of Energy project. So we have one part of INCITE, of this INCITE. There's tons of other projects in different fields. But one of the things we got the opportunity to is to actually use the DOE Summit computer, which is I think number 5 or on top 500 these days. So I want to talk a little bit about about what is the actual challenge that we face doing this and discuss some preliminary scientific results. We are still looking into this. So the INCITE project is operated there, and we have previously used INCITE by Niels Wedi from ESMs to get an allocation to use Summit for a 1.4 uncoupled atmosphere model. So that's definitely quite innovative in the sense that we could actually now run a global model at us. We like to say call it a kilometer, but it is actually 1.4 kilometer, and it does make a difference. But it was quite nice to be able to do it. But we are already now at the stage at ESMs where all our model runs are coupled. So doing uncoupled modeling is a little bit last year, okay, second to last year in this case. So we had a chance to actually start trying to do a coupled one. We have already shown in many cases that we get a benefit of coupling for the NWP problem. And one of the cases where we do get a lot of benefit is for tropical cyclone. So we focused this study on studying 4 tropical cyclones, Irma, Florence, Trinity, and Ida, and those were based on the fact that we could actually get ocean data to validate the ocean response. Doing all those storms, the Hurricane Hunter, together with the US Navy Academy, have been deploying Alamo floats in front of these so we can actually see what the ocean is doing at very, very high temporal frequency. So we have a chance not to actually validate if the couple's response is accurate. And also about the same time we have been installing a 4 new ATOS cluster in our Bologna data center. And we actually were able to get one cluster as my sort of personal machine for a week, which is a lot of computer resources. I will probably never get that again. So our coupled model, Jano kind of described most of it. Of the component, we have the IFS models, which is, I think, I would like to stress, it's not just our model, it's jointly owned with Metro France. So it's a collaboration. We create cycles of this model together with Metro France every year. We have a wave model, and we have an ocean model. And we use NEMO as our ocean model. We tend to use a fairly old version of operations. In the process of introducing a new version with a new grid, and in this case we're also exploring a higher resolution than where we use 1/12 of the degree, which is not bleeding edge resolution in NEMO, but it's high resolution compared to a quarter degree. There's a 36th of the degree which other people are able to run, but we are not. So here's a list of all our operational systems just for reference. The only thing I will say here is that the 9 kilometers sort of our baseline production one we run. We have an ensemble of 18, but 9 kilometers would be sort of standard for all our NWP models. Actually, probably sorry this year, not next year. So I took something wrong. So we do actually use the sequential coupling. As Oliver was just mentioning, we run the atmosphere. Then we run the wave model, and then we run the ocean model in one executable, on the same course. And so this is a repeat from actually 2017 workshop, but not all of you were here at that time. So what we do is we have basically within NEMO coded capability that we can call NEMO from the IFS time stepping through subroutines. So the IFS will call an ocean model and integrate time step the ocean model and get fields back. But the IFS don't know anything about what is in NEMO. All arguments all information from the IFS is part of subroutine, but the interface layer have full access to all the NEMO modules. So yeah, so maybe get on to some of the more interesting stuff. We don't actually really within this system concentrate so much on generating weights because we assume we can do this from something else. We just use script convention as a sort of standardized way of getting weights from somewhere else. And the sequential, and I think I already mentioned that we run on the same MPI task and OpenMP thread. So this system will work well in the case where all models scales well and can use the same resources. If they can't, then they can't. If one of the model doesn't scale, so if let's say we need many more processors for the atmosphere, we have a small ocean. But if it doesn't scale and it actually starts to fall off in the scaling curve, it will not work well. And this is a real limitation. So what were we actually trying to do? So we were trying to run one of limited set of start dates for about 7 days for run length. So this is a medium line in WP. And as I mentioned in the beginning, this thing about model days per day, we tend to say we have to do a 10-day forecast in 1 hour, so that's 10 model days per day. And the reason why I'm saying this is that when we look at these two systems we're running on the HTOS machine, we ran all the sort of serious resolution, and I will actually show this because the actual resolution, but it's a 1279, 255, and 399 grid with a quarter degree and 12 degree ocean. All this could be easily fit into immediately a new ESMs cluster which is 1600 nodes. But about a quarter of one of these clusters, this sort of 4.5 kilometer with a 12 degree ocean takes about 3 hours to do it 7 days. So this is obviously not fast enough. So we are more or less able to, on this machine, to run, if we want a full cluster, do one forecast cast in 1 hour. So it's kind of almost within what's doable. But if we then go to Summit, where we ran the really high resolutions and runs one thing is, in order to use some of the efficiently, you really have to have GPUs. This is a GPU machine with a CPU attached to it. I mean, the IBM Power 9 CPUs are still fast, but the NVIDIA Volta GPUs are where the real workhorse of that machine. And we have a part of this is a spectral model, and the spectral transformer, the one thing which takes up a lot of time. So that's the part we have been able to port to the GPUs in this instance. But for this system, we managed to set up, and so this is of the order 9. So we have managed to run this on 960 nodes. This is about a quarter of a very large machine. And then this forecast takes 18 hours to do 7 days. So this is about 10 days per day. That's very far from a target of 240 model days per day. So my point with this is that this is a resolution. It will take a very long time. I'm not even going to guess it before we'll get a machine we can afford to run it on. So just to use an example, so this is 9.4.5, 2.2, and 1.5 degree resolution, number of grid points. We were stuck with a wave resolution of about 0.05 because that was the highest one we have managed to create at some point. But this is a lot of grid points. You really see how this goes up. So this is the number of grid points in one on one surface grid.
Even for the ocean, 15 million.
I think so. Maybe I made a computation mistake. Yes, it's 2 million, and then times 8. That kind of works.
Okay.
So the sort of scientific challenge we had this is First of all, we really didn't want to do the quarter-degree model, which we want to do. So we wanted the 1/12 degree. We actually ideally want a 1/36 of the degree, but we don't know how to run that. So that means we have to switch to our development version of NEMO. How to do good ocean initial conditions? That's because we tend to run ocean at this data simulation, etc. So we did something to do a registration of this. So do something quick and fast to get it running. We also really wanted a non-hydrostatic atmospheric model. That didn't work at the 1.4 kilometer model for reasons which we don't understand yet. And also one of the things you might want to switch off of this resolution is deep convection. But we actually didn't switch it off completely. We only switch it off, reduce the effect of it. Okay, technical challenges. I'm aware that I'm running a little bit late. Sorry about that. The biggest change about this problem at Summit is just to get enough GPU coverage in your code to actually make it worse using a machine like that. In terms of more direct technical thing with coupling, you end up having something like 36 gigabytes of NetCDF files for the whole for the weights, and that's a lot of data. If we now, as in our case, has to read this on all MPI tasks in order to figure out how to do the whole communication. So actually, how many MPI tasks you can have per node is not great. So in our system, we reached the high watermark very early in the code. I mean, we deallocate the data when we don't need it. But we implement a very simple solution to we know the decomposition of the model. We can compute the communication patterns offline and once and for all for a given decomposition. And then we just read it in. And this is not elegant, but it's a practical way of getting things run for one very quickly. I mean, I.O. we are facing all of us I.O. and challenging thing. But there was also a technical issue here. I mean, Summit uses GPFS as a file system. ATOS uses Luster. Some of the techniques to have many readers to read data and works fine on GPFS in general. GPFS is not stable always all the time. Luster don't like this. And also the practical thing is we actually processing these model outputs is so time consuming. Okay, so I think I'll skip this one in the interest of time, except for one point. Even with when you run on Summit on all these many nodes, the orchestral was a very cheap part. So that includes all the coupling and everything. So there's no direct really thing that is very bad in terms of limiting the scalability of a quarter-degree model on this amount of nodes. It actually runs fine. Fine. We don't have this sort of that the coupling exploded and we can't do it. We can. Okay, some science results. Is just as okay. I already talked about the I/O. But one of the things which we really need to start thinking about when we do high resolution model runs is to move the diagnostic into the model rather than trying to interpolate some observation point, etc. when we run the model, because it's just the data there. We can use full temporal and spatial resolution since it is in memory, rather than trying to read and interpolate. For instance, that's one of the things we've been using. We use this one for NEMO. That will probably be the difference between having the information we need to compare with these Alamo flows or not. It's just a sort of thing is if you actually try to run an uncoupled model here at 1.4, even the 2.8 kilometer resolution, you get core pressures of tropical cyclones, which are unrealistically physics, because the mechanism of feeding back into the ocean needs to be there. And sort of when we have this fully coupled system, what we do see is we get much better winds, we get much better core pressure. So, I mean, it's not just lower core pressure and stronger winds, it actually fits with observations. So this means that the model can actually do this simulation extremely well, and resolution will help. Okay, I could also just skip this one. So this is two. See, let's an interest time to just take the high one. This is actually work. Maybe that solves the problem. Okay, it doesn't work. That's fine. Fine. You can see it. It's in the slide here. So what we have to do is that we have managed to write one global coupled simulation with very high atmospheric and somewhat high, but not very high ocean resolutions. So that means now we can start addressing science question about what is the actual benefit for, I mean, tropical cyclone was the focus here. We can now start running other cases, but it will always be a per case basis. We cannot in any way afford to do a proper statistical evaluation of these systems. It actually kind of worked surprisingly well with our system. The only real problem we had was the sort of initialization phase was extremely slow, and we did this workaround to actually compute this these communication patterns, because then we never needed to read the weights in. We are still really, in order to use a machine like Summit, lacking better GPU enabled code in the IFS. It is, and it's taking a long time to get where we are now with the spectral transform, and we need to do a lot more work. So, and in the sort of very long-term future, we are considering at ESMWF to be able to run different part of the whole, have an infrastructure where we can put different parts on different hardware, both within one cluster, but possibly heterogeneous clusters. I mean, a simple example is we probably will keep NEMO on CPUs for the time being, but move to GPUs, move NEMO's GPU with Cyclone at some point. But we are in this phase of change where a heterogeneous machine with GPUs and CPUs will be our next machine. So it'll be very interesting to see our next machine. This new ATOS, we have one cluster with GPUs, but it's a CPU primary machine. The next procurement is going to be interesting, and we need to be ready for it. Thank you so much.
So, I'm Sergi. I come from the Barcelona Supercomputing Center, and I will present an automatic approach to balance computer system models. This will be more primarily focusing on the performance, not hardcore performance, but execution time and the coupling cost of these kind of applications. At the end, trying to save energy and time on our execution. And now, of course, I've got the problem. Okay. So, you already know that. Their system models are commonly built from different components, and I will be talking specifically about the multi-program, multiple data approach. And the problem with that is that the components exchange information during the simulation, and when they have different calculation time, this synchronization creates a waiting time in one or more of the components involved, and this reduces the particle efficiency of the whole model. This is normally called a slow imbalance, and it really, for me, has two main factors. The first is the dependencies, which I just components reads. Sometimes we can have online diagnostics, different output configurations, and at the end, these interactions can become really complex, and we lose some performance. And the other, which we don't talk too much, I think, is the parallelization. And this is the fact that the components might not be able to run at their optimal scalability points, but rather at the point that is optimal for the whole execution. The way that we normally deal with that is, for the dependencies, is try to come up with a setup in which all the components run at the same execution time, as this would ensure, in theory, that there is no waiting time. So we have here the execution time in blue for two components. They are not the same, so one of the components has to wait for that amount of time, and we try to find balanced configuration, so to minimize that waiting time. And how fast should we go? It is common to use just a threshold on the parallel efficiency of each one of the individual components, and this can be 50, 70%, it depends on who is doing the test, but yeah, this is how we select how fast with the configuration. But as we will see, current methods to find this optimal configuration can give suboptimal solutions. And in this work, I will first define a metric to evaluate the performance of these coupled ECMs, and also to have some control over the energy time trade-off that is commonly happens in MPI. Then create a methodology to find the better resource allocation. So at any point, we are changing the sources of the model, but only how many processors are we using. And finally, try to build all this methodology as automatic as possible, as to require the minimum user impression as possible. So yeah, this is what I dream. Is you start with an experiment with a poor load balance, then you get the scalability properties of the individual constituents, and then you enter this method where you first run a prediction script, it's Python tool, which will take the individual scalability properties and try to predict what is the best combinations of processors for the components involved. And then an automatic iterative process, which is the one that will actually submit experiments to the HPC platform, get performance metrics from real simulations, and at the end modify processor allocation to reduce the coupling cost. And the outcome of that is a balanced experiment. The method has been used to optimize different configurations of ECR3 in Mare Nostrum and also in ECNWF machines. So yeah, I will be mainly talking about the most used configuration, which is NEMO and IFS. NEMO using the standard resolution is 1 degree and 80 kilometers for the atmosphere, IFS, and the coupling frequency is 45 minutes, and everything handled by Oasis. Now, a few words about the performance metrics. This already you know, but to mention them, this per day, this will be the metric of the time to solution, the core hours for the metric of the energy to solution. They are both related with this equation. And then to know what is the total execution cost overhead due to the coupling events, we have the coupling cost. This includes the waiting, rereading, and also the sending of the data. And this is a nice overall metric to know how much are we losing coupling, but it's really hard, but it doesn't tell us what is the bottleneck. So maybe it seems like can be NEMO in this case in the middle, because it's the component that is waiting more time, but rearranging the coupling cost formula, we can come up with a component coupling cost, which is exactly the same metric, but now for each one of the components. And that helps to know, it's, yeah, basically the component that has more coupling cost is the one that we should prioritize when trying to deal with these complex simulations. They are all add to the coupling cost, but now we have that at the end it was not NEMO, but another component because it was using more processors. And then for the trade-off, energy time trade-off, I came up with this, let's call fittingness metric, which is a new metric that allows to have this control over the energy and time trade-off. It's at the end just a weighted sum of the simulated years per day and the core hours per simulated day. And the weights are the time to solution ratio and energy to solution ratio, which both have to add to unity. So why should we use that? When we've got the different scalability points for a component, we normally have the table, then we build this type of plots, and then we can start saying, okay, it seems that after 800 processes, it's not scaling. It seems that, well, we can start talking about this plot for a while and then choosing one by just looking at this graph. But with this metric, you can set up, for instance, a time to solution ratio of 0.5. That means we want to prioritize as much the speed as the energy. And you have a value between 0 and 1 that tells you, in fact, what is the point which is optimal under that weight. So, for instance, that should be 432 processors, but you can change these weights, and now you can have a more energy to solution oriented setup, or you could do the same, but for a more time to solution oriented. So with that out of the way, I will talk about the method itself. I already introduced it a little bit, the Bayesian script. So we start with the scalability of a couple of components. We have NEMO and IFS simulated per day at different processor counts. And the first step is to combine all the possible combinations that we have with both components. With this, we can create a table. At the top, in the horizontal, we have the NEMO processors, that we have IFS processors. And the values in the table are the simulated years per day of that combination, assuming that the couplet execution speed will be as fast as the slowest component, which is like the ideal. Then, using the equation that I described above, we can have exactly the same table. This matrix would be the energy per simulation. Now we have the core hours per simulated years per day for all the combinations. With that data and put it in place, we can come up with the fittingness metric, and that shows in yellow the best combination of processors for IFS and for NEMO, which in this case is 528 for IFS and 288 for NEMO. But the problem with that is that we are just predicting our results based only on the scalability properties, and we are not taking into account the real interactions between the components. And of course, we expect some variability when running on the HPC platform. So instead of just selecting the setup which maximizes we take, for instance, 5 possible solutions as optimal. And this is when we enter the automatic iterative process, which is the one that will run on the HPC machine, the 5 possible setups or optimal setups. It will get the performance metrics with Lucia, which is the internal OASIS tool to get some of the performance insights, and then modify the setup to minimize the coupling cost using the component coupling cost that I described also above. And this process is repeated over time, and at the end you end up with optimal configuration. And now we will discuss just briefly a couple of results. The first is the standard resolution experiment in Mare Nostrum 4 machine. It is the same experiment that was used for the SMIP6 exercise. And I will show how we find out a better parallelization for the execution, and we will contrast that with other traditional methods. And the other is a standard resolution experiment in ECNWF, and we will show how the fittingness metric can help us to end up with a more energy or time to solution setups for the same experiment. So yeah, the original setup, this experiment was used to simulate over 14,000 years and consumed more than 50 million core hours in Mare Nostrum 4 back then. So this was really carefully made up so that it was like the optimal path at that time. As we see, the optimal that we achieve is a configuration which is not only 12% faster, but is also 5% less costly than the original. But as you see, the coupling cost is almost the same. So the benefits from here are only coming from the parallelization that we are using, not from the dependencies. We could not improve that. Probably it was already optimal. We still have some coupling costs because IFS has some radiation in some time steps, and these irregularities in the time step pattern creates that, well, it's basically impossible to have zero coupling cost. If we compare this configuration with another using the same parallelization, which we say it's optimal, but now using that approach where you have both components running at the same speed, you end up with a configuration which is still better than the original, but as you see, the coupling cost grows, and yeah, it's suboptimal compared to what we have found. And then for the experiment in ECNWF, the original setup was using very few resources. So when we came up with the optimal one, it was 56% faster, but it was also more costly, 2%. So we could say that this is a more time to solution oriented setup. It's using more than double resources. So we have just executed the workflow again, but now setting a time to solution ratio of 0.2, so prioritizing the energy. And at the end, we end up with a new configuration, which is 24% faster, but maintaining the same execution cost as compared to the original. So to conclude, the load balance is still one of the key limiting factors of co-better system models performance, and current approaches to find the resource configuration can not lead to optimal setups, and setups that normally involve manually trying out different configurations, and it can be very repetitive, tedious, and prone to error. And this auto load balancing method has achieved better setups for experiments that were used in the past, like SNP6, and in multiple resolutions and different HPC platforms. For the future, we expect our system models to keep growing in the number of components and complexity that they have. And without the proper tools and metrics, these traditional approaches would not even achieve suboptimal solutions. This workflow method has proven to work with 2 components, but we want to, of course, extend that to handle more complex simulations. So that's all. Thank you for your attention.
Okay, so hello everyone. My name is Arnaud Caubel. I work at IPSL. I will present you an ensemble simulation that have been done with the IPSL model. The ensemble simulation have required some development and modification in the model. Okay, so to start, some general information about the model. So this is the IPSL coupled model in its ocean atmosphere configuration. It is composed of LNDZ as an atmospheric model, both for dynamics and physics, on a long lat grid. Orchide as a land surface and routing model. NEMO in its version 3 for ocean, LIM3 for sea ice, PSCES for biogeochemistry, OASIS3 MCT as an ocean atmosphere coupler. XIOS in its version 2 as an IO server, and the libGCM, which is the running environment we use at IPSL. This model runs in MPMD mode, one executable for LNDZ Orchide, one for NEMO, and one for XIOS server. We have hybrid parallelization for LNDZ Orchide, MPI OpenMP, and MPI only for NEMO and XIOS server. This model has been intensively used to participate in SNP6 project with production of SNP6 publication data ready files. It is used for many studies from paleoclimate to future projection. It is used at many horizontal from 500 kilometers to 50 kilometers and vertical resolution with 79 levels. And it runs only on CPU's architecture, both on Intel and cores. We are working on the development of the next version of the model. The main changes are concerning Dynamico, which is the new dynamical core which runs on icosahedral grid. And we still use LNDZ as a physics model. Orchide will run also on icosahedral grid, and we will have a new routing model to be able to use this routing model in the land surface model on icosahedral grid. We will use NEMO in its version 4 for ocean, and CI3 for sea ice, still Pisces for biogeochemistry. This model has been already used for CMIP6 IS-ENES3 project in its atmosphere-only configuration, different horizontal resolution from 200 km to 25 km horizontal resolution. The scientific validation is in progress at low resolution for the ocean configuration. And this model runs obviously on CPU's architecture, Intel and AMD computing core, but there is a work to target new architecture, and especially CPUs. The work for Dynamico has already been done. This work was based on OpenACC directives, and the work is in progress for LMDZ or KID and OPA components. So let's get into the subject of the ensembles by defining what is the difference between a standard simulation and an ensemble simulation. A standard simulation is when you have only one instance of your model, which run over a period, and which follow one trajectory with regard to a given score. And on the other hand, ensemble simulation consists in running several instances or members in parallel and periodically selecting and cloning with perturbation trajectories which go in the favored direction. Favored direction which is measured by a score function. There are many possible protocols to use for ensemble simulation to generate different members, initial condition, parameter, forcing. And here I will speak about only initial condition. And on the figure, you can see that you have, for example, 3 members. That means 3 different trajectories. And with regard to the score, over a period, we will kill the first one, we will clone the second one, and we will decide to continue the third one in order that we'll have still 3 members for the following period. Concerning the IPSL model, what does it mean to run ensembles with IPSL models? Each member of actual IPSL model produces its own output files. That means if the number of members increase and becomes big, you will provide a lot of inodes on computing center file system. And that could be a problem because we have a strong constraint on quota of inodes on computing center file system. So a post-processing step would be needed in order to pack output files to reduce inode footprint. But this kind of post-processing step may be very loud, especially in terms of size of temporary buffer, computing resources, and also time to solution to obtain what you want. Another topic is the handling of perturbation of initial state. There is no existing automatic functionality to do that in the actual model. So that means there is a high risk of some errors with many members, because if you want the perturbation by hand, it's not very secure. So we have to adapt our model to be able to write out data from all members of a component into one single file. And that means this file, we will have a new ensemble dimension. Also, we want our model be able to synchronize all members after a given period. Also use an external tool to determine good or bad trajectories to extend and to select with regard to solving function. We would like also automatically perturbate initial state if needed. And finally, easily define the number of members that could be divided into pools by specifying the number of pools and the size of the pool in a parameter file. And that means we have modifications in OASIS, XIOS, and the IPSL running environment. Now, what about this modification we have to do? Concerning ensemble management into XIOS and OASIS in order to output one single file, some words about communication between models OASIS and XIOS in IPSL model. The handling of MPI communicator is done by OASIS. That means MPI local communicator of the model are created by OASIS at initialization phase of the coupling to allow internal communication of the model. And that means also MPI intercommunicator between XIOS and the model are created also by OASIS at initialization phase to allow communication between XIOS and the model. But this functionality is only available for two models. So, since we want to output data from all members of a component into one single file with ensemble dimension, we need that XIOS server communicate with all members of a component. And so, we need to have an MPI communicator containing all member process of a component in order that the calls to XIOS subroutine are collective for all members of a component. This implies the development of new functions, new subroutines in OASIS to allow that. And this development was done by OASIS team, and is the last version of OASIS, as Sophie mentioned yesterday. And also, we needed to develop a new dimension ensemble in XIOS, which will be handled as an axis in XIOS. So in the figure illustrates an example with two members. And so we can see a communicator which contains all atmospheric members, another communicator contains all oceanic members, which communicate with XIOS server. And to do that, we use only one NAM-coupled configuration file for OASIS. Concerning perturbation, so we want to be able to perturbate the initial state. So we have implemented a functionality to perturbate the starting state of an NDZ atmospheric model in the dynamics part, based on white noise on potential temperature on all points of the domain. And this perturbation is specific to one member because we want different perturbation between members. And finally, we have also to adapt IPSL running environment to handle management of execution of all instances, all members of IPSL model over a period in the same computing job. Members are divided into pools, so we will define some ensemble parameters, defining the number of pools and the size of pool. The member of a pool run at the same time, and the pool run sequentially one after the other in the same job on a given period. There is a figure at the bottom of the slide which illustrates that. We want also the handling of restart file to allow the continuation or stop of a member. Also, the possibility to use an external tool for the selection of the member. And at the end, the handling of perturbation to be applied or not to a specific member. In order to summarize, this is an overview of the final ensemble's workflow with 3 steps. The first one is the simulation of all members, pool after pool, over a period in the same computer. Then, second step is the selection of good members by computing a function score on output data. And then the third step is the perturbation based on a white noise into initial state of the new member. And after that, it starts again at the beginning for the following period. So now we have a tool to perform some ensemble simulation, and we will use it in some application case. The first application case concerns paleoclimatology study, and especially the reconstruction of 1,500 years of paleoclimate. This is something which is led by Myriam Caudry at IPSL. The configuration of the model will be at a very low resolution, that means 200 km for ocean, 400 km for atmosphere. One instance of this configuration run about 800 cores at 48 simulated years per day. And to do this case, we need to run 80 members of the model to run and synchronize a given period. We will use the data simulation method to select the different members after every simulated year. And the output data will be aggregated on the fly by XIOS into one single file. The result, we divided the 80 members into 8 pools of 10 members, which run on about 8,000 CPU cores. Obviously, we gain of a factor, we had a gain of a factor 80 for the number of inodes. The time to solution for one pool does not depend on the size of the pool. This is nice. And the time to solution of all members is depending on the number of pools. For example, at the end, the best case that you could see here at the bottom of the slide takes 4 hours with 8 pools with 10 members per pool. That means that takes 4 hours to run 80 members. There is a very small additional cost in time to be taken into account between two periods, because you have to handle the restart, you have to select, you have to use the tool for the selection, you have to perturbate, and obviously that depends on the size of the pool. At the end, you obtain only one single file. This is very nice for the inodes, as I told you before, but it's also very useful and very nice for analysis. You have only one file. And also, this is useful for low resolution that uses few cores, because that allows to benefit from computing hours that are usually reserved for application using several thousand cores. For example, the praise call in Europe. Another application case, also led by Myriam Caudry, same idea than the previous one. This is a reconstruction of last 130 years of historical period. Now we use the low resolution version, not the very low, but the low resolution version at 100 km ocean and 200 km atmosphere. One instance of the model run on 1,100 computing cores at 28 simulated years per day. Before we need to run 80 members of the model. We will use the same data assimilation methods and protocol of selection than the previous case, and also we have output data aggregated on the fly by XIOS into one single file. The result will divide the 80 members into 10 pool of 8 members, which run on 15,000 CPU cores. Obviously, we have a gain of a factor 80 for the number of nodes. The time to solution for one pool does not depend on the size of the pool, but very, very good. And the time to solution of all members is depending on the number of pools. Here, the best case is to have to run during 8 hours to run all your 80 members. Another application case, we have seen that it's used for paleoclimatology and also present day, but now there is also an interest to use the tool in extreme event. And this is an ongoing work done by Robin Oyel at IPSL. The goal is to simulate heat waves and therefore to select periodically the best trajectory that can cause heat waves. It's just starting, but this is the idea. The configuration to do that will be an atmosphere-only configuration at 200 km horizontal resolution. And the idea is quite different than the one before, because here we want to run between 100 and 1,000 members, but with selection every 4 or 5 simulated days. So the integrated period, the simulated period, is very short here, rather than before the simulated period was 1 year. My last slide. So now some conclusion and perspective. That was a nice and effective example of collaboration between tools and also teams, OASIS and XIOS. The contract has been fulfilled. There is no impact on the inode created for output file when you run Ensemble simulation. That could be very useful, especially for low resolution, to target allocations reserved for many thousand computing cores. And the question, what about operation or reduction between members? Useful in such ensemble. There is a functionality to allow reduction between members with XIOS, which has been already developed by NCAS at Reading. But there is no the possibility to output in one single file. So the objective of the development was a little bit different. In the actual version of IPSL model, it is possible to do some reduction operation between members, but only between members of a pool, and not between all members. Here, a constraint. Reduction and operation between members could have an impact on the time to solution, because in the actual model, they are performed on model or client side. That means a synchronization of all members is needed to do some reduction and operation. Some modification were needed into the component to handle parameters concerning the handling of number of pools and size of pool. So it is not plug and play. You have to modify your component. So that would be better to be less invasive in the. And to finish, the ideal would be to have asynchronous services, XIOS, dedicated to such operation or reduction between different members. These kind of services are not yet available, but possible in the new XIOS version, the XIOS-3. And I invite to attend Jan Marnoswaf's talk tomorrow about that.